Alright, so we came up with one solution called the Peterson solution for our critical section problem. But we know that if this solution is valid, then these three constraints must be met, no? So we'll see if they are met or not. So mutual exclusion is preserved. What does this constraint mean? When one process is executing the critical section, no other should be allowed. Let's go back to our solution. When you see this while condition, this turn equal to j needs to be true. So if turn is offered to j, only then j can execute its critical section. Similarly, if turn is offered to I, only then I can execute its critical section. And because turn can either be I or j, only one value, either 0 or 1, not both, at any given point, only one process can be executing its critical section. Hence, mutual exclusion is preserved. First category, check. Second, the progress requirement is satisfied. What does this constraint demand of us? If no process is currently executing the critical section and then some process comes up and says I am ready, that process should be allowed. So again, going back, let us assume currently no process is ready. So flag of I is false, flag of j is false. So nobody is executing their critical section, right? And then process I comes up and says, my flag is true, I am ready to execute my critical section, but I will offer to let j go first. Now j is still not ready, flag of j is false. So this loop evaluates to false, or this condition evaluates to false, so this will not happen. I will immediately be allowed to execute its critical section. Same thing vice versa, right? So if neither of them is ready, and then one of them comes up and says I am ready but I will still allow the other to go, then you will not allow the other to go because the other is not ready. So your control shifts back to the former and the former is immediately allowed to go into its critical section, which means progress requirement is satisfied. Third condition, bounded waiting requirement must be met. So what does this condition mean? So when one process is executing the critical section, the others are waiting, right? So they should not be made to wait indefinitely. There should be a bound on the waiting time. How do we achieve this? Back here, once the critical section is executed, we set flag of that process to false, meaning that process says I am not ready for my critical section now, meaning I don't want to execute it anymore. So because flag of I is false, next time when you check, when the other process comes and checks for flag of I, that will be false. So I will not execute its critical section, instead j will be allowed to execute. So basically, once a particular process has done with its critical section, it is saying I am no longer ready or I no longer want to be entering that section anymore. So once that announcement has been made, the other process, if it is ready, is free to immediately go and start working. So it does not have to wait indefinitely, because as soon as a critical section is executed completely, this announcement will be made, which means bounded waiting requirement is also met. So that is our Peterson solution, and we see that it is a very valid logical solution because it satisfies all our three constraints. The only problem being this works only for two processes, and it's not very likely that in a computer you will have exactly two processes at any given point of time. You're definitely going to have more. So we need to come up with something that is equally efficient and logically sound, but also works for more than two processes. So for that we have other solutions which we'll look at in the upcoming segments.